One more time. Hey, everybody. How are you? Let's see if this thing's working. Has to be on first. That'll be helpful. Okay, good. Let me just quickly mirror this, and then we are in business. All right. Oop. Okay. If you didn't already get a lollipop, feel free to grab one. I'm not sending a message when I brought Smarties last time and Dum Dums this time. Here's this. That's just what the candy's called. Okay. I encourage all of you today to open up a lecture notebook while I work through the slides. And it looks like this thing is out of battery. So I'm going to switch to the other. Yeah, so I'd open up a lecture notebook at the same time because the slides are essentially in exactly the same order. So rather than go through them twice, why don't you all sort of take your notes in the demo notebook and you can play all of the code that I show you in the slides. So I'm going to recommend. I'll go to the demo for a couple different things today, but for a lot of the code I won't. So just keep in mind, that's the recommendation. So welcome to lecture 3. Let's go ahead and dive right in. So some announcements. First of all, our first assignment is already due. Lab 1 is due tomorrow. Labs are not like homeworks in that, the answer is given in a video, a walkthrough in the lab. So, the goal is really learning. It's not necessarily problem solving. You can do it without that sort of solution to help you. But just keep in mind, those are still due. So you want to get those in. Monday and Wednesday discussion starts today. Today's discussions are open attendance. So you can attend any discussion you want. Okay, you can attend any discussion you want. Are people hearing the mic or just my voice? Is it going in and out or no? It is going in and out a little bit. That's not good. Let's see. Has enough battery. Let's see. We're going to have to do our best here. All right, let's go with this and see what happens. Yeah, make sure to watch the discussion mini lecture before the actual discussion. That's just to prep you so that they can jump right into the material. You can see Ed for more details on all of this. Mega discussion, data scholars discussion, online discussion have sort of a special flair to them. Online discussion is really reserved for people who cannot come to campus regularly. So most likely, if you are in this room, you should not be going to online discussion. Just keep that in mind. Catch-up sessions also start today with Sammy. Those are going to be 4 to 5 p.m. on Mondays and Wednesdays. Attendance isn't taken or anything like that. Those are also open attendance. Highly recommend you check those out. Sammy's putting together a lot of wonderful custom material for those sessions. Staff office hours starts today in Warren, which is across campus. Really nice air-conditioned building. I guess that'll make more sense when it warms up a little bit. And then also there's going to be online office hours in the evenings. So just keep that in mind. You can check the website for hours. And then like we mentioned in the last couple lectures, Michael and I have office hours around the corner every single lecture. So after every single lecture for an hour, we sit in a room, at least one of us, and we have a wonderful discussion. So far, our office hours have been a lot of fun. Please come by. We've talked about a lot of great things. Okay, so that's not what I wanted to click on. Let's see what this thing's doing. Okay, agenda for today. We're going to be talking about more Pandas stuff. So we're going to start with conditional selection. So let's see what's going on in conditional selection. So to review from last time, we learned how to extract data a couple different ways using its integer position, remember iloc, and its label using .lock. And so here's an example. Here's an example of extracting some information. So the first 10 rows of the baby names data frame, we can extract by using .lock, where we say we want everything up to row index 9, and we want all of the columns. But before I sort of jump ahead here, I want you to ponder for a moment. If we replace .lock with .iloc, or we took away the .lock entirely and just made it context-dependent extraction, would we get the same result back? And this is a nuanced enough point that we probably wouldn't test it on an exam. Okay, it wouldn't be a huge issue, but think about this for a second. It's actually implemented in the demo, so maybe we switch over to the demo really quick to see what would happen if we used something else here. So we're going to run the demo. This is the same demo linked on the website. You go right to the lecture, click on code. This will come up. Okay. So we're using a data set of baby names from California. There's a lot of fancy code here to import the data that's out of scope for Data 100, but you're welcome to go check out. Ultimately, you just want to run that line, or rather that code cell, to get this baby names data frame back. And you can see we have a baby name for a particular year, for particular sex in California, and how many people were born with that name. Okay, so that's our data set. That first slide, we were selecting the first 10 rows using .lock. So this is exactly what we just saw in the slide. When we use .lock, we select everything up to row index 9. So we start at 0. And with .lock, we included everything up to 9. Okay, it was inclusive, and then we got all of the columns. But if we change this to .ilock, and we use integer location, that's how Pandas is going to read it differently, notice now we only get everything up to 8. .ilock is exclusive, .lock is inclusive. You can almost think like .lock when you're putting stuff in it, it's like you are going to get what you tell it, right? If you mention a 9, it will be there. But with .ilock, it works a little bit more like range in Python. If we take out the ilock and the lock entirely and just use context-dependent extraction, which is sort of the most common way to do something like this, what happens? Nothing works. Why? Context-dependent extraction only expects one argument. What happens? We only get up to 8. So context-dependent extraction is also exclusive of that 9. Again, nuanced point, but just keep in mind, when you're doing exploratory data analysis, these sorts of things can happen, and I want to give you a sense of how you can debug things going into the future. Okay, so just a little point there to make before we jump into the full lecture. Okay, let's keep going here. So we're working with just these first 10 rows. How would we extract, instead of just the first 10 rows, actually choose something based on a condition? How do we choose something based on a condition? For example, what if we wanted to select all rows where the particular value in a column was greater than 5? And so we saw, I think, a little bit of this last time, but .lock and this context-dependent extraction also allow you to put a Boolean array inside. You can do that Boolean masking that we saw with series. That works as well with data frames. So let me give you a little bit of a taste of what this looks like, sort of expanded out in sort of an ugly way here. So we have that baby names first 10 rows data frame we were just working with. And what we're passing into it is a 10-element Boolean array here, lists in this case, right? We have an inner list, we have inner brackets, we have a list with true, false, true, false, true, false, all the way to the end. And so what are we going to get back if we try to extract information like this using context-dependent extraction, just the brackets? Well, the first element is true, so our Boolean mask would say, yes, grab the first element. Second one is true, right? Fourth one is true, sixth one is true. We're only going to grab those elements. Anything that's false gets masked away. And so if we run this, we end up with just the rows index 0, 2, 4, 6, 8. So we're able to construct Boolean arrays and use that to filter our data frames and also filter our series like we saw last time. This is a very important step in the data analysis pipeline. We need to be able to select particular rows that meet some condition. Okay? All right, we can also do the same thing with .lock. Notice the code looks very, very similar. You actually, we saw last time, don't even need to necessarily include that colon. .lock will automatically insert that colon. It'll assume the second argument is a colon if it's not provided. But notice this also just works with .lock, and it works in exactly the same way. Okay? So we're going to be working a lot with those Boolean conditions today. So we can also generate these Boolean arrays by performing different operations on series. We can try to ask, does the series, is it greater than 5? Is it less than 10? Is it equal to some value? And we'll get back a Boolean array. So notice now we're looking at the sex column in the baby names data frame, and we can see that in this particular data set, at least in those rows, we only have an F category for female and an M category for male in this particular data set, right? If I ask the question, okay, when is baby name sex equal to F, I'm going to get back a Boolean series. I get back a Boolean series. Again, we're only seeing a couple of the elements here, but I could then use that to go and filter my original data frame. I could use that to go filter my original data frame. So just to give you a description here, Anytime the sex is female in this original series, we're going to get true. Anytime we have male, it's going to be false. These ... mean that there are a lot of other values in the data frame. Anything risky about looking just at an output like this and making assumptions about the entire data frame? Very similar to what we talked about with head before. The idea here, those first 5 rows, those last 5 rows might not be representative of the whole data frame. So I always want you to be thinking about this. When you get this nice collapsed output, it's really nice on your computer to see that in your console, but don't start making too many assumptions. You gotta be careful. You gotta be careful. Okay, so then what we can do is actually pass that array right into our original data frame. We're going to use context-dependent extraction and pull out all of the rows corresponding to female. So that inner array is the same thing we saw last time. We're extracting now all of the rows where the sex of the baby name is female, probably recorded from the Social Security Administration. And what do we get back? We get a data frame, notice now, where all of the sex, at least that we can see, is now female. And before, some of those were male, and so we're reasonably confident that we're now only pulling the rows where the sex is female. Okay, so this is an example of Boolean masking on a data frame using context-dependent extraction. Do people actually say the word context-dependent extraction when they're coding up? No. They just index for it. Usually people, when they're indexing into a data frame, are just using brackets like this, and they never say the word context. Okay? Okay, let's continue. What about this? Same idea with .lock. Again, if you didn't include the colon, you would be fine. .lock will automatically insert it for you. But keep in mind for this class, and just generally good practice, .lock and .ilock have 2 arguments. What rows do you want? What columns do you want? In this case, same idea. We pass it the Boolean mask for the rows, and then we say we want all of the columns. So same idea for .lock. We saw this, same idea. Okay. So we can also combine different conditions. So let's say I want all of the rows where somebody is marked as female, and they were born in a particular year, or after a particular year, or before a particular year, or within some range of years. We can do all of this in pandas. We can do all of this in pandas. So we can use the AND operator and the OR operator that you're familiar with to say whether 2 conditions are met or 2 conditions are OR. So for example, we could say, let's go grab all of the rows where the sex in the baby names data frame is F, and the year is before 2000. So what we've done is constructed 2 series now, 2 Boolean series of trues and falses, and then we are saying or element-wise. We're doing it element-wise. So we look at the first element of each thing. If this one's true, this one's false, then the whole thing becomes true. We work our way down through both of these series to get a new series that we then index into baby names. So notice now, we're only going to get rows where the sex is F, and notice now rows where the sex is F or, so it doesn't have to necessarily be true, both of them, right? We can still have M in one column, or they're before the year 2000. So notice all of these are before the year 2000. We don't have any male rows that are in like 2022, like we saw in the other slide. Okay, so things you've seen before in some shape that we're now sort of massaging into this pandas workflow. All right? Okay, so other operators, they look a little bit different than maybe what you've seen before. You know all of these operators on the right. You might not know exclusive OR. Exclusive OR just means, is the one on the left true? Is the one on the right true? But they both can't be true. We're excluding the case where they're both true. That's XOR. But by and large, you're going to be using these first 3. I almost never use exclusive OR in my code. Okay, I'm usually just explicit, and I say this or that, but not both. Depends on what you prefer to do. But notice negation here is a little tilde. In other programming languages, negation can be something a little bit different. All right? So you can start putting these together to start making different Boolean conditions to filter your data frames. All right, we have our first Slido today. Let's try this out. So I'm going to hide that little thing at the top so you can see. But why don't you give this a go? And feel free to talk with your neighbor on these Slidos. Pull up the demo. All of the Slidos are implemented in the demo, so you can start playing around with the code. It's good to think about these first before just running the code and getting the answer. Remember, the point of Slidos is not just to get them correct. These aren't graded on correctness, but it's to actually understand what's going on under the hood. So give this a go. And I can also come around with questions. To pretty verbose code. So if we look here, notice we're starting to check whether a particular data frame has all of these names, right? We want to grab all of the rows where the name of the kid is Bella, Alex, Nargis, or Lisa. These are people who've taught the class in the past, okay? But even though this works, it's starting to get kind of verbose, and we're repeating ourselves a lot here. This isn't like a great way to write code, right? If we wanted like 10 names, it's starting to get really, really nasty. And we're going to learn lots of different techniques in this class for collapsing what could be really nasty code otherwise. So how can we handle this? So it turns out Pandas provides lots of different alternatives for doing conditional selection, aside from just your standard and or equal sign, greater than, less than. These are just a couple ones that you should know for this class. So we're going to see .groupby, .filter in the next lecture. That's sort of our capstone pandas lecture, where we're going to be doing grouping, which is a huge part of the data science workflow. But .in and .str .starts with, let's quickly talk about now and see what these look like. So what is .is_in? So this is on the Data 100 reference sheet, by the way. So anything on the reference sheet, again, usually shows up on exams, and then anything you need on an exam that's not already on the reference sheet will typically also put on the reference sheet for this year. The reference sheet for this year isn't up yet. It's usually produced right before the exam. So how does .is_in work? So we can do this with those names we just saw. So if we have a list of names, we have a list of those 4 names. Instead of asking whether name is equal to each of those names and then using or, we can just ask the question, well, does that series fall in the array or the list containing all of these names? And what we're going to get back now is a Boolean. This is going to give us a Boolean series that is true when the baby name is one of those names and false when not. Okay? So if we look at this, most of these are false. Those 4 names, not super common, at least in the 10 rows we're looking at. Again, you might look at that output right there and think, oh, there must be a bug in my code, I'm getting all false. But just remember, we have a lot of rows that are obscured here. Something to keep in mind as you're working on data science projects. Okay, what about .str.starts with? So we're going to see more about this .str accessor in lecture 6 when we talk about regular expressions next week. But just know the reason why there's a double dot here is you're saying to your data frame or to your series, you're saying .str, we're going to use a string operator. Hey pandas, we are about to use a string operator. And so when you use .tr, it opens up all of these different string functions that you can use on a particular series. And then if you do .starts with n, it's just going to pull all of the names that start with n. So just know when you're doing string manipulation with a series, you have to use this .str accessor. And then you get all of these nice string methods you can work with. Again, we're going to see more of that in lecture 6, but we can see now we get this big Boolean with all of the different names that start with n. Okay, so there's lots of these out there. There's lots of these out there. .is_in and .starts with tend to be pretty useful, especially .is_in. I'd say that's one of the most common ones that I use. You're often checking whether a particular value falls within a particular array. Okay, and there you go. So if we look at this data set now, if we pass in this Boolean array for every name that starts with an N, we can see all of the names here now start with N. So you know it works. Okie doke, let's keep going here. Adding, removing, and modifying columns. Super, super common things to do in data science. How do you tack on a new column to your data frame? How do you change an existing column? How do you remove a column? How do you modify it? Let's see what this looks like. So if we want to make a new column, let's say with the number of characters in each name, so my name's Josh, I want a column that says 4 when my name is up, Josh, that's 4 letters. So how would I do that? Creating a column in Pandas, pretty straightforward. You want to start on the right and work your way to the left. So how does this work here? On the right, we can see that we have a series with the length of each name. So there's that .str accessor again, where we're telling the series, hey, series baby names name, all of the names, that column in the original data, we're going to apply a string method, and the string method we're applying is the length of that string, the number of characters in that string. So I now have a series that for each name I have the number of characters. And then second step here is I'm going to create a new column called name lengths, okay, in my baby names data frame. So I'm writing out the new column that I want with the original data frame, and I'm just assigning that series to it. Okay, nothing crazy here, nothing crazy. And now, if you look at this data frame, we can see at the far right, we have all of our names. Mary, also 4 letters. We can see we now have a name lengths column. So that's how you add a column. It's very similar to how you modify a column. Let's say I wanted to modify that name length column. Let's say I wanted to just subtract 1 from all of those name lengths for some reason. Maybe all of the names in this data set had an extra period at the end or something like this. I wanted to subtract 1 from all of those names. You might guess it's exactly the same as before, very similar to how you might change a variable. We start with our original name lengths column, we subtract 1, but then we have to reassign back to that same column. So we can overwrite columns using exactly the same notation as creating new columns. Okay? Important thing to keep in mind for pandas, and we'll see this in a bit. You usually have to reassign back. Things don't usually get modified in place. Pandas likes to create copies of things. You have to reassign those copies back to the original data set. Keep this in mind. We'll see this in a little bit, explained in more detail. So notice how has our data set changed now. We started with name lengths all being true. Now they all have 1 smaller value. Okay, so we now modified the data frame. We have another one, .rename. This one's on the reference sheet. So if we want to rename that column, let's say instead of name lengths, we're going to go put this in a public database. And so name_lengths is useful for us while we're coding, because we don't have to press the shift key and strain our pinkies, right? We don't have to special space and deal with like weird backslashes. Let's say now we were putting this in a public database and we want to change the name to something more human readable. We can use the .rename method, where we specify in this columns argument, we have to specify which columns, some dictionary that says, how do I want to change my existing names into some new names? And every time I use this function, I switch the order of those 2 things and mess it up. Forgive yourself. Do forgive yourself. That's a very, very common typo. So now if I run this, what happens? Everything that had the name lengths has now been switched to length. So if we want to rename a column, we use this .rename method with a dictionary. Okay? A couple more before we have another Slido that I'm hoping will be okay this time. So let's see, the .drop method. .drop, sometimes you want to get rid of columns. One thing I always like to remind people, again, I like to give like little data science tips that aren't part of the standard curriculum here, is anytime you're getting rid of data, like .drop, or when you're filtering out data in a real data science project, you always want to be really, really careful. I often change my data science workflow to just ignore a lot of that extra data I don't need as opposed to dropping it. Because very often you'll be in your data science workflow, you'll get to a point, you dropped your data at some point in the past, and then you realize later on you actually needed that data. Or you don't realize later on you needed that data, and suddenly your analysis is biased because you no longer have all the data you need. So just keep that in mind. You know, dropping seems like it makes a lot of sense. Just get rid of columns, right? To get rid of different rows when we're filtering things out. Just keep in mind, I always like to say, when you're removing data from a data frame, be very cautious. Be very cautious. I've been burned by that many, many times before. But how do you drop if you actually do want to drop? Okay, by default, the drop method will drop rows. So if I did not include this axis equals column argument, pandas would go look for a row with the index called length and drop that row. Okay, we have to say, use the column axis. You might also see axis equals 1 in a lot of code. You can also write axis equals column. So notice we're waving goodbye to the length column. What happens after we run this code and reassign to baby names? We now no longer have a length column. Okay, so we're getting our sort of toolkit together. Again, memorizing all this syntax is not the goal of the lecture. It's more just understanding that we have all of these methods at our disposal, and being able to describe what we want is more important than precisely how to code it. Right? That's why we have the reference sheet. That's why we can look up syntax on the fly. We just want to understand what can be done. Okay. I think we have one more before our Slido. Let's see. We might have a couple. Okay, so on the previous slide, we reassigned. This was that point I was making about copies before. We reassigned baby names to an updated data frame. Notice what we did. We dropped the length column, but then we reassigned back to baby names. We didn't just do dot drop. Why did we do that? Let me show you. So if I just were to run baby names dot drop with length axis equals column, so notice what's going on here. I'm running some code. I write dot drop. What that would do is print out, if you were to put that bracketed code in its own cell, it would print out a data frame that didn't have the length column. But then if I printed out baby names, the original data set that I supposedly dropped length from, the length column would still be there. Okay, the length column would still be there. So pandas does not act on data frames in place in memory. When you act on a data frame in pandas, it creates a copy of that data frame. This is sometimes called copy on modify. Okay, it creates a copy of that data frame, and that's what gets returned. So if you refer back to the original data frame, it's not going to be changed unless you overwrite it. Unless you overwrite it. There's also an argument you can use in most pandas functions called in place equals true, where you modify an object in place without creating a copy. For the purposes of data 100, I don't recommend using that argument. And I try not to use that in a lot of my workflows because it can be kind of hidden. This makes it really obvious on the left side of your code, you read left to right, that you're overwriting the original data. But if you have some sort of like memory constraint or some problem like this, where your data frame that you're manipulating is really, really large, it might be better to modify in place. For the purposes of data 100, don't worry about it. Okay? All right, we have a diabolical Slido. Let's give this a go. I'm gonna give you all a couple minutes. Please talk with your neighbors on this. Let's see, no, this one's good?
The code here and the code in the top right normally are different. So to
weird.
this Slido, you're going to want to use this new QR code.
This code works. Okay, okay, cool. Okay, and then the other one is
The other is also
is having an issue. All right, maybe I'll debug it while working on this. All right, give this a go. Are people getting into this one? Yes, yes, good. All right, great. Okay, give this one a go. I'm going to give you a couple minutes. This is a tough one. This is a new Slido. Again, is this something we would give you on an exam? Probably not. This is not like a very productive data science style, learning question. The goal here is for you to really play around with some of the techniques we just talked about. Okay, so feel free, talk with your neighbor, think about this. Again, the demo has this implemented if you want to play around with it. So I'm still hearing a lot of talking, which is fantastic, and I want you to keep going here. People have submitted responses, but I also want you to get a chance to do the other Slido because it's good practice, and then we can take a break, and then we'll come back and actually work on both of these. So I'm going to shift back to the Slido, if that's okay, just to see. Let's see if you sign in, you'll be able to work on it because I want to give you a chance to try it out. Avert your gaze when the answers show up for a second. I don't know if they will. Um, There we go. Oh, avert your gaze. Okay, there we go. Try this one. So if you give this QR code a scan, tell me if that's good now. Let's see. As usual, if you got questions, raise your hand. I will come around and we can talk it out. And again, no need to whisper too. Full volume is totally fine. Totally fine. My favorite sound is a lecture hall talking raucously. And we're going to take a break right after this. So when you finish your Slido, feel free to get up, stretch. Maybe we'll resume in like 3-4-ish minutes here. Okay, I recommend having the demo open. I'm going to go switch over to the demo. Let's talk through both of these Slidos. And thanks for being flexible working on both of these with me today. All right, so the first one, first Slido, we're trying to count the first three baby names, or excuse me, grab the first three baby names where the count is greater than 250. So more than 250 people in that particular year in California with a particular sex had that name. And it's the first three that just appear in the data set. Okay, so let's see the first one here. So the first one, we're using iLock. Let's see, why is this no good? Thank you, thank you, one sec. That's fine, expected. Okay, so the first one here, okay, we're using iLock. So we're grabbing integer locations. Remember, they are right-hand exclusive for a slice. That's the thing with the colon. If you actually provide a list of numbers to it, it's not going to just exclude the right-hand side of that list. So we're saying now, okay, two arguments to iLock. The first one is all of the row indices as integers. So the 0th row, the 233rd row, and the 484th row. That looks like what we're looking at there. And then we're also grabbing the third and fourth columns, where the first one starts at 0. So if we go look at the baby names data frame, okay, we have the 0th column, the first column, the second column, the third, and the fourth. We want the third and the fourth. That's indeed correct. So that first iLock should work out for us. Good. Second one. Okay, now we're using .lock. Okay, .lock usually expects two arguments. Usually expects two arguments. If it doesn't get a second argument, what does it assume that second argument is? Colon, good. Colon. We already don't want all of the columns, so we know that's going to be wrong. Let's try it. What happens? We get those rows, but we have all the columns. That's not what we wanted. That's not what we wanted, but want to understand why the incorrect answer is wrong. That is a big skill that I think is criminally neglected. When writing an exam, picking easy answers or picking the correct answer is quite easy for an exam designer to pick the easy answers. The hardest thing to design when you're writing an exam are the wrong answers, because you need to pick something that'll sort of put somebody, make them a little bit confused, and it's still incorrect, right? So don't ever neglect the incorrect answers. Just because you know why something is correct, make sure you know why the other things are incorrect. Is there a hand here? Yeah, go ahead. Sure. So good, this is an excellent question. So .ilock, isn't that exclusive for slices? So it's exclusive for slices, that's indeed correct. So if I were to say instead, let's grab everything up to 9, it's going to give us everything up to row 8. But it's only exclusive because that's a slice. It has that colon in it. Because we gave it an actual list with what we wanted, it's going to give us everything. The exclusivity is only with a slice. Good? Okay, great question. Okay, let's keep going. What else? So .lock. We've got .lock now. So again, two arguments here. We're saying Boolean, grab everything where the count is bigger than 250. That sounds right. Grab just the name and count columns. That's sounding pretty good to me too. And we're grabbing the first 3 rows of that data set. So I mentioned last time I often prefer sample over head when I'm exploring a data set. Head is very useful when you're when you're intentionally trying to grab the top of a data set for some analysis. Let's say you want the highest number. Often I'll do the head of just one value and grab the very top of a data frame. So here's a very good use of head. Let's see, what do we get? That looks good to me. Okay, as usual, many different ways to do the same thing. Okay, fourth one, excuse me, we're grabbing everything where the count column is greater than 250. Boolean array, that's good. And then we're grabbing the name and count column, that's the same as before. But now we're saying from that, okay, from this list where the counts are all greater than 250 and we just have the name and count column, we now want to use iLock, where we are grabbing, and this comes back to the question over here, we are grabbing everything from 0 up to the second row index. So this is 0, this is 1, and this is 2. And we're grabbing all the columns. But if we run this, we only get 2 rows. Why do we only get 2 rows? iLock is right-hand exclusive with a slice. Okay? Great. So that's the first Slido. That's the first Slido. Let's go ahead and move to the other Slido. And feel free to raise your hand if you got questions. You can also ask them on the Q&A in Slido, and Ella here will get an answer to you. Let's go ahead and now talk about this diabolical Slido. This is the first time folks have done this in class. Hopefully fun diabolical. Okay, so we have a 3x3 data frame all filled with A's, B's, and C's. The column names are A, B's, and C's, and the indices are also all A's, B's, and C's. So how do we start working with this thing? So we have a couple different responses to deal with. So the first one here, we're sort of chaining together commands, and that's exactly what it's called in pandas. When you start using multiple commands, it's called chaining together methods. So what are we doing? Well, we're doing df.dropb. If I look at this data frame, when I read df.dropb, my mind automatically goes to dropping columns. But remember that .drop by default drops rows. So df.dropb is going to drop the B row, not the B column, not the B column. And so then what happens after that? Well, then it's going to go grab the A column. So we're going to get back C and A now. And we're grabbing the first element of that series. We have the values on the left and the index on the right. That's going to give us A. Oh, let's see, A, not B. Don't worry about the warning message. Okay, so how do we fix this? What do we have to say here? Axis equals columns, because now if I drop the B column, okay, and I go into the A series, that first element is going to be B. Let me just show you this step by step so you can see it. Oop, delete this, sorry. Okay, then we're going to go into the A column, and we're grabbing the first element, so that B right there. So that will give us B with a nasty error message I haven't seen before. Don't worry about that error message. It's just a warning. Code still runs. Okay, make sense? Easy typo. Easy typo to make when you want to drop, use axis equals columns. Okay, let's do the next one. Let's do the next one. I'm going to print out this data frame again just so we have it right in front of us here as we solve this out. No, let's not enter passwords here. Okay, so what are we doing now? What are we doing now? How do we sort of read this code? So let's work our way from the inside out. That's a useful way to debug functions. So one of the first things we're doing here is getting a Boolean index because we seem to be indexing into df. So let's actually even go check if that's a Boolean index. So the first thing we're doing is grabbing the A column, CBA, and then what we're going to do is go check which values in A fall in either B or C, are equal to either B or C. And so if we look just at that A series, we have CBA. Confusingly, it has exactly the same index. And then we're asking which of those values is a B or a C. And so if I run this, I get back true, true, false. Because if we look at that DFA, notice the first two elements are C and B. And both C and B fall in that list, B or C. There's a match. So we have true, true, false. We're now going to use that true, true, false as a Boolean mask to the original data frame. So I'm now going to take that original data frame and I'm going to pull the first two rows and exclude the third row. I'm getting back the first two rows of that data frame, true, true. That's what's getting passed in here. And I'm not getting the last row of the data frame. Okay, then what are we doing? We're using ilock, and we're saying go grab the element that's at the 0th row in the first position. That's a B. That's a B. Okay? Clarification questions. Clarification questions. I recommend stepping through this on your own to see. Again, is this the kind of question we would ask on an exam? No, right? We're going to be working with real data sets on the exams, but I want you to understand how these functions work. I want you to understand how they work. Okay, and limits we have in lecture. We want to use smaller data frames. Okay, and then the last one. The last one, what's going on here? We're actually renaming some columns in the data frame. We're renaming some of the columns. So let me print out the original data. What are we going to do here? We're going to rename the columns. The B column is going to get renamed A, and the A column is going to get renamed B. We're not going to switch any of the values in those columns. Okay, notice the values in the first two columns are exactly the same, CBA, BCA, but notice the A and B have now switched. The A and B have now switched, and now what we're going to do is go grab the location corresponding to the row label A, and this column label B. Column label B is now right here. That looks like an A to me, and indeed we get back an A. Okay? Good? Important thing here is being able to read code, see what it does, run it, eventually get to the right answer. Okay? Good. Nice work on those Slidos. How are we doing on time? We got a half hour. Let's keep going. A couple more Slidos to do after these. I think just one. Okay, so the correct answer here, first one, second one, and then the last two. Or at least those, sorry, not in that order. These first two are correct. Okay, we did very well here. For the baby names question, and then for the other one, how did we do? That one's a lot harder. Good. Good work. Okay. All right. Keep going. We had our interlude. All right, some useful utility functions in pandas. So everything in NumPy, for the most part, you can use in pandas. Everything you've learned about NumPy is going to readily apply to pandas. Okay, we learned a little bit about NumPy in Data 8. And again, a lot of the stuff you can learn on the fly. Don't necessarily worry about knowing every single NumPy function that's out there. I don't think anyone does. So what could we do? Well, here's an example. So let's say we want to generate this Yosh count data frame. How are we going to do that? We're going to index into the baby names data frame to every row where the person's name is Yosh. Where the person's name is Yosh, not to be confused with Josh. Okay, we're going into the baby names data frame and we're pulling out the count column. We're not running a count function or anything like this. We're just pulling out this count column. And if we pull out just one column, we get back a series. And presumably, there's a lot more years in that data set. We're going from 1910 to 2022, but there probably, or it seems like, there weren't people born with the name Yosh in a lot of those years. We're only seeing years where at least one person had the name Yosh. If I take the mean of that series, I don't have to say extract the values and then take the mean. Pandas is smart enough to just take the mean of all the values, and I get this really long decimal place. So this happens by default in most programming languages, is you're going to get all these degrees of precision. And a lot of people on their homework write down all of these degrees of precision, thinking that I want to be really, really precise because that makes my answer really, really precise. Just keep in mind, there's a note at the bottom here, another data science pro tip. Don't report more precision than you need. More decimal places aren't necessarily impressing anybody. If anything, they can be kind of annoying and hard to read. When I look at that number, my eyes don't immediately just see 17.1, right? I see all these numbers and I kind of have to sort out what actually matters. So just keep that in mind. By default, you're going to get a lot of decimal places. But when you're reporting something, cut it down, right? In this case, 17.1 is probably enough. We don't need more than one decimal place here. And then the max of the Yosh count is 29 here. That's the largest value. Notice these NumPy functions, NP, import NumPy as NP, they're going to work on series. Okay? All right. A ton of other utility functions. I know I keep stressing this, but pandas can do so many different things. If you want to manipulate data in some specific way, somebody probably already wrote a hyper-optimized pandas function that does exactly what you want and more really, really well. Okay? That's used so infrequently that if someone reads your code, they probably will have to go look up what that means, but they'll think you're so smart because you pulled out this really specific function. Okay, so there's an enormous number of these utility functions. These are the ones in Data 100 we're going to use quite a lot. Okay, size or shape, describe can be really helpful for exploratory data analysis. We'll go through each of these and then we'll do a Slido. So the first one, .shape and .size. These are attributes. These are not methods. Why are these attributes? Notice there's no parentheses after them. These are stored as numbers inside of the data frame in series objects. This is already sort of pre-computed and just hanging out inside that object. Methods are functions that are applied to something in that object. Okay, so the .shape attribute is going to give us the dimensions of the data frame as a tuple. Okay, pair of numbers here. We have the number of rows and the number of columns. That's on the reference sheet. And then there's also .size. .size for a data frame, not the most useful thing. It's the number of rows times the number of columns, or if you have a multi-dimensional data frame, something we're not going to work with in Data 100, it's going to multiply, all of the rows by all of the columns. Okay, so .size for a data frame, not super useful. .shape, super useful. For a series, you're going to use .size all the time. For a series, you're going to use .size all the time. Both of these on the reference sheet. Okay, .describe. .describe is supposed to be useful for exploratory data analysis. And it can be. If I run .describe on this baby names data frame, I get a nice new summary table, notice with a lot of decimal places, for all of the numeric columns. So notice we don't have state, we don't have sex, but we do have year, We do have year, which I don't know if it makes sense to be computing an average of year, but they're going to do it for us because it's numeric. And we're getting a bunch of statistics about count. And at sort of first glance, like this seems like it would be very useful, and often it is, but keep in mind it's not giving us any information about the other columns called categorical columns. We'll learn about different variable notations on Monday. Okay, so what I often do in my analyses is after all the years of like running custom summary statistics for every data set, I've actually just written a custom function that does all the summary statistics that I want on a particular data set. And so you can go look up if someone's written one that you like, you can write your own custom function for doing this, but .describe has its limitations. Okay, I don't use it very often. All right, sampling. I mentioned this before in the context of exploring data using .head. So to randomly sample rows from a data frame, you use the .sample method. Makes sense. And by default, you're going to sample without replacement. We're sampling without replacement. What is sampling without replacement? Bunch of balls in a bag. I reach into that bag. I pull out a ball. I sample a ball. Sampling with replacement says that I put the ball back in the bag when I pick the next ball, so it can be picked again. Sampling without replacement means I can only select a ball once. Okay, so by default, it samples without replacement, which I think is a good default here. So for example, I can run babynames.sample. That's going to sample one row without replacement, which is identical to sampling one row with replacement. That's exactly the same process. If you just want one thing, you can use .sample, but you can insert whatever number you want here to sample a particular number of rows. So df.sample10 will give you 10 rows, or df.sample5 will give you 5 rows. Okay, and if you want replacement, you have to include the replace equals true argument, which we'll see on the next slide. So again, pro tip, we mentioned this before. df.head, when you're actually exploring data, can be kind of misleading. The top of a data frame isn't necessarily representative, whereas df.sample, if it's randomly sampling, will give you a better idea of what's going on. Okay, just a little pro tip. Okay, pandas methods can be chained together. I mentioned that word before. They can be chained together. So for example, I can use two methods. I can write babynames.sample5, give me 5 rows, and then go grab every single row, and then the second indexed column all the way to the end. Okay, so that's one way to chain. Let's say you have a really long chain. It is really hard to read a chain that goes all the way across your screen. Okay, so typically in pandas, what we do is we write these sort of data pipelines where each row gets its own method. And how do you make sure you can work over multiple lines? You can put like a line continuation character at the end of every line. Gets really ugly really fast. And so you'll often see this notation where you have some object and you're setting it equal to some long chain that you start with parentheses and end with parentheses. And by starting with parentheses and ending with parentheses, pandas knows to just keep reading. When you hit the end of a line, just continue it on to the next line. So that's a very, very common notation, and you'll sometimes see, 10 different operations inside of those parentheses. And it's nice because it kind of reads like a sentence. First, we're gonna go grab all of the rows where the year is 2000. Then we're going to go sample 4 rows with replacement, which is hard to see whether we sampled with replacement here because none of those rows are duplicates. They could have been duplicates. Okay, but as it turns out in this particular sample on the slide, they were not. But there's the replace equals true argument. And then finally, we're selecting those same couple rows. Okay, so very, very common notation. You might see that in your homework. You might want to use that in your homework rather than write, again, just a single line of all these chain pandas commands. It's much harder to read. It's also much easier to debug this way too. Okay, one of the nice things you can do is like comment out individual lines and then see what happens. When you have everything in one big line, it's kind of tricky. You have to delete pieces. All right, series.unique. What do you think this does? We pass in a series. It's going to give us all of the unique values in that series. This comes up all the time in data science. We very often want to go grab the unique values in a particular array. We'll see in the next lecture when we use group by, this sort of happens by default under the hood. Okay, but a very common operation, if you just want those unique values, you can use the .unique method. Okay, let's say you want to say something about those unique values. Let's say you want to count how often they appear. You can use the value counts method, which is sort of a shorthand, again, for this grouping operation we're going to see in the next lecture. So what's going on with value counts? Value counts is going to tell you how many times each of those unique values appears in a series or in a data frame. Okay, so if I run baby name name and do value counts, I'm going to get back a sorted series. So by default, it's going to sort it for me. Excuse me. It's going to sort it for me. Okay, and I'm going to get a series back. You're always going to get a series back from value counts. Okay, that tells you how many times each of those names appear. So it looked like Gene appeared the most often. It was pretty popular, or at least mentioned at least once for the most years, whereas Theon was just showing up towards the end, probably because of Game of Thrones, right? Okay, that's value counts. That's value counts. And then we might just want to sort. How do we sort? We can use something called sort values. We can sort values. So when you sort a series, it's pretty straightforward. There's only one set of values to sort on. When you sort a data frame, you have to specify which column you want to work with. Okay, so if I want to sort a series, I just write sort values right after that series. Notice it's by default sorted in ascending order. Ascending order. So if I want it in descending order, starting with the z's and working my way down, okay, how do I do it sort of descending? I can use the argument ascending equals false. This is an annoying thing in every language. In R, you specify whether you're descending. In Python, you specify whether you're ascending. When people are reading your code or when you're reading your own code, you might forget, are this sorting in ascending or descending order? For that reason, I always like to, in my own code, be really explicit. So even though ascending equals true by default, like we have on the left, I like to always say, am I ascending? Am I descending? When I use sort values, so that when I'm reading my code later, I don't have to think so hard. You want to think about your future self when you're coding. Okay? And notice we specified which column we sorted on. All the other columns are ignored in the sorting. One other thing to keep in mind, and this is going to come in handy in the Slido we're about to see, is notice that it's not like we get a new index. The original indices are all preserved when we sort the values. They are just listed in the sorted order. The original row labels stay attached. Keep that in mind for the Slido. And there's the Slido. Let's give this one a go. If you've got questions, feel free to ask. I will come around. As usual, talk with your neighbor. No need to whisper. Full volume is just fine. we talk? I'll leave this live so you can keep entering some answers here. But let's give this a go. Let's give this a go. Okay, so notice the example data frames I gave you. You'll see in a minute. They are a little misleading. I'll show you why in a sec. Okay, so we have a simple data frame here that I gave you in the demo to help you think about this. This is just a data frame, not necessarily one that's going to give you the right answer. So let's see. So we have a data frame with column A, 2, 3, 4, column B, 3, 5, 5. Pretty straightforward. So first one, we want the rows where the values in column A are at least as big as the smallest values in column B. Looking at this first one, these are the values in column A. This is the smallest value in column B. Let me convince you of that. 3, .min. That is a built-in method. We could also have used numpy.min. That's fine. That works too. A lot of these pandas methods are very flexible. Don't be worried about breaking stuff. Try it. See if it matches your expectations. Ask an LLM, right? See if it tells you, yeah, it's probably better to do it this other way. Can anyone think of a reason why dfb.min might be preferable to np.min? Not for computation reasons, but again, just like as a data scientist, making your life easier. Why might dfb be a little bit better? Or just make your life a little bit easier? Yeah. Yeah, perfect. So we look at this, and the first thing I think is I want the smallest value in B. So I start with B, right? In a sentence, start with B, dfb. Then I want the smallest value of B. Then I do .min, right? So this sort of pipeline approach to pandas is really nice because everything kind of reads like a sentence. Everything reads like a sentence. Even though something else works, totally computationally fine, you will have the right answer. Someone reading your code will know what's up. For your own benefit, sometimes it can be nice to do things like .min. Now keep in mind, there are other NumPy functions that are not built in like this. .min is just one of the NumPy functions that is indeed a method of series. It's a method we can do .min of series. Not all of them work like that. You might be stuck with doing numpy dot some fancy function. But just keep that in mind, little tip. Okay, so if we run this, what happens? All of the rows are A, are at least as big as the smallest one in B. Smallest value in B is 3. Both of these rows of A are bigger. Good. Next one, more complicated. DFA is bigger than DFB, sort values ascending equals false. So ascending equals false means that we are descending. And so the largest values are at the top. The largest values are at the top. If I select the first element here, 0th element, what is that going to return? 3. It's not going to return 5. Why is it returning 3 and not 5? Look at those indices. All right, look at those indices. 3 is at the very bottom, but it has an index of 0. Remember, with context-dependent extraction, it's looking for the label 0, not the 0th element. If we had used iloc, I don't think it would have worked because it's a series. Okay, but we're looking for the index labeled 3. Again, is that something we test on an exam? No. Is this something you could run into as a bug? Absolutely, right? Is understanding this going to help you on the exam? Sure, being more familiar with a lot of these concepts. Okay, so just keep that in mind. That's not going to work. That's not going to work. Okay, even though it gives us those same rows, this is a little bit misleading. For this specific data frame, it ends up working out, but there's no guarantees that the 0th index item is going to be the smaller. So let me just give you an example here. What if I change this to 7? What if I change this to 7 and I make this like a 2? Okay, I'm going to change that to 7, make it a 2. So now, notice that the smallest element in the B column is not the first one, it's the second one. So let's see, the minimum is now 2. If I filter to where the rows of A are at least as big as the smallest in B, I get all the rows back. If I sort values, ascending equals false. Okay, notice in this case that the 0th element in this case is 7. So it's not going to give me the same result here. Okay, so even though it worked out with the example I gave you, in general, it won't. Okay, and then last one here. value counts with tail, another sort of weird use of a lot of these. So dfb.valueCounts, if I call dfb.valueCounts, what happens? I get the number of times each of the items in B appears. So it'll make a little bit more sense if I revert B back to its original form. Let's do that and come down here. So notice in the series 355, 5 appears 2 times and 3 appears 1 time. If for whatever reason you wanted to turn that into a data frame, there's that function toFrame from last time you could start messing around with. Okay, but don't worry about that for this lecture. Okay, and then if we said dot tail n equals 1, what would happen here? So dot tail will give us the end of that series, and it's just going to give us one element from the very end. So what do we get back? We get the very last element of that series that has the value 1 and the index 3. If I run this, I get an error. Python doesn't know what DFA should be compared to. That whole thing is a series. Okay, we can't easily compare all of the numbers in A to that series. We can't easily compare all the numbers to that series. I would want to compare to the 3, which is the index, right? And so just for the purposes of this problem, we could sort of massage out that index. If I write .index off that series, I get this nasty index object, but notice stored inside of that index object is a little 3. Let's try that and see if this works on its own. Will it be smart enough to know to just use the 3 inside of there? Sorry. Still not smart enough. So then how are we going to pull it out? Well, maybe we can go pull out the first element of that index. That looks like a 3 to me. Okay, again, is that a realistic thing that you'll necessarily be doing on the fly? No. Is it useful for understanding how these functions work? Yes. Notice there's a lot of massaging going on in data science. This is very common in exploratory data analysis. When you're writing production code, the massaging isn't so great, right? Because notice that is not the most readable code. There's probably a better way to do that, right? But when you're working on your own, you might be doing lots of massaging like this. Okay, let's go ahead and go back to the lecture and we'll wrap up with custom sorting and then just a quick taste of what's coming next time. Great. Okay, custom sorts. Custom sorts. How can we sort a data frame? We've seen one approach. We've seen one approach where we just dump in a column and say sort on that column. But let's see how we can modify that approach a little bit. So one approach we could do that's very similar is just create a new column, which we know how to do, and then sort on that new column. Okay? This is all code you've seen before in some context. We're creating a new column called name lengths that's made up of all of the names where we just get their lengths. We use that .str, that string accessor, which opens up this world of string functions, one of which is the length function. And then all we do is sort that baby names data frame by that new name lengths column, and we're going to do it in descending order, overriding the original baby names data frame, and then we're grabbing the first 5 rows. So it looks like these are the longest names in that database. Francisco Javier, Ryan Christopher, John Christopher. Okay? Let's keep going. What's another way? So another thing we can use is called a lambda function or an anonymous function, which I think is covered in 88C and 61A, albeit briefly. And if not, we'll get you there. So a lambda function is sort of a one-off function. It's an anonymous function. It doesn't have a name. There's no reason to save it in your code. You sort of write it on the fly so that it can be used, and then your code won't use it in any other place. Again, we don't need to sort of keep it hanging around. So what can we do in this case? We can do everything in just one line. Take the original baby names data set, sort it by the name column, and instead of using the actual values to sort that data frame, I want you to modify those values first. But I want you to just temporarily modify them just for the purposes of sorting. How are you going to temporarily modify those items? Well, what I want you to do is apply the string.length function to each of the elements. So for each element in that series, get its length, and then sort based on that result. Okay, sort based on that temporary column that's created in the background. And if we do this, we should get the same data frame. I'm realizing that a different thing might have been passed into on the back end when I copied in this photo, but we should have exactly the same data frame. Okay, notice we're seeing some overlap. I'll fix that after the lecture. Okay, same exact idea though. We're creating a temporary column in the background using this anonymous function, this lambda function, this temporary function. Okay, that's another way to do it, using a custom sort. And then finally, we can use .map. And this isn't something that's covered really in depth in Data 100 beyond just this application. But this idea of mapping over an iterable object in Python, some kind of list essentially, this idea of taking a function and mapping over that whole list, very important concept in data science. Entire frameworks are written just to do this in faster and faster ways. You may have heard of MapReduce. Mapping is a big part of this. Okay, so the series.map method, let's say we want to sort that baby names data frame by something arbitrary. Let's say the number of DRs and the numbers of EAs in each of the names, the number of DRs and the number of EAs in the name. So we actually write a function. This is not an anonymous function. This function is actually saved in the code. Okay, we've written a function that takes a string and just counts the number of times EA or DR appears in the name. And then what we're going to do is take that name column and we're going to use this .map method, which is useful in lots of different contexts, not just sorting. But we're going to start with the names from that baby names data set. We're going to map over that entire series. So you can imagine we have our series, and we're now going to apply our function to each element of that series. We're going to map over that series. Okay, important concept in data science. We map over, that creates a new column with the number of DRs and EAs in each name. And we can see we created a permanent column here. This isn't a temporary column. And now we could sort directly by that new column we just created. But it's just a nice little introduction to this .map function. And then also with lambda functions, you might be recalling now, or if you saw it for the first time, totally fine too. Okay, all right, we're just about wrapping up on time here, but I'll just give you a sort of taste of what's coming for next time. And perhaps if you want, you can review Data 8 materials on this. But next time is sort of our capstone lecture for pandas, where we're actually going to be doing, not that we haven't been doing data science, we're really getting to the point where we can start doing damage when it comes to exploratory data analysis. I mentioned this in the first lecture, but grouping and aggregating data is a huge part of the data science workflow. I mean, literally, just the idea of grouping your data into separate groups like this, and then aggregating each of those groups somehow to form a new data set. This is like such a big part of data science, I can't even emphasize enough this next lecture. So you covered this in Data 8, and you might want to go review it. But it's this idea that we choose a column to group on. So for example, the ABC column. We group on that column. Every unique value of that column now gets its own group. That's what I mentioned before with uniques being important. Each unique value gets its own group, and this is all happening in the background. Okay? Each of those groups is sort of a little sub-data frame in the background, a little sub-data frame that's been tagged with that group label. And then to each of those sub-data frames, we want to do something. We want to apply some aggregation function to those data frames. In this case, it looks like we're grabbing the minimum of each column. Once we've done that, we then bring all of the data frames back together into a new final table. What you see in Python is straight here from here. You don't see the middle step going on in the background, but you have to understand what's going on in the background to really grok grouping. Okay, why don't we go ahead and end there? Thanks, everybody. I will see you tomorrow, hopefully with some new candy.